Hi, my name is Avishek Chanda. I'm a PhD student at the Department of Mechanical Engineering with the University of Auckland, and my today's topic is the effect of flammability on flammability of plywood structures. Uh, so the basic outline of the presentation includes background, a bit of objective, the materials used, the results, and the final conclusion. So the background of plywood or wood is basically it is a composite material, which can be classified as a natural composite material because it has lignin matrix and hemicellulose fibers embedded in it. So the current applications of plywood, as you can see, include kind of monotonous applications in furnitures, in houses, and things like that. But it is monotonous; it doesn't have its own shape. So our main aim will be to make shapes and then see the fire properties. And when it comes to fire, plywood is basically a combustible material, as we all know. Any wood, we think of that, but it is actually has very good fire properties. And if we can somehow enhance those with fire retardants, we can actually have a very good uh, material for use. So the basic method used in the current uh, for the current presentation is the cone calorimeter test. We'll be doing all the experiments in this cone calorimeter that is available in our department, and we'll be using the ASTM 1354 standard for correlating all the results. So the main objective of the current presentation or the current study is to form successful geometry shapes and see how the flammability is affected because of the formability. So the material used for this is radiata pine or Pinus radiata, which is widely available in New Zealand for commercial use. So we will be using the same in our current work. So basically, we will have first done a very elaborate statistical analysis on the parameters for forming. So we have done a V bending test and then a 4-point bending test to form the top head section, and then finally see how what are the springbacks that we get, and we have tried to cancel that springback through a change in the legs and given a 7.5 degree inclination into the leg, and the final structure has a 7.57 springback, which actually is 0.45% different from the desired geometry. So it gives a straight channel or a straight compartment. So basically we'll be using the same method for making our compartments, and these are the two types of compartments, the formed ones and the glued ones. The glued ones basically represent the traditional compartments where we have glued it using Addo's glue, and then we have gone into bigger samples to see whether there are any differences when the sizes of the samples change, and then finally we have done a corrugated and honeycomb core experimental simulation, and then seen how it actually performs when compared to a fire retardant composite material. So this is the cone calorimeter used, and when it comes to results, as you can see, the horizontal test results for 100 cross 100 compartments under 35 irradiance kilowatt per meter square irradiance shows us that there are significant differences when it comes to formed and glued samples. The formed sample has a shifted HRR trend with a later ignition time, later peak release rate time, less smoke production, similar kind of heat release, and later flame out time as well. Only the peak heat release rate is a bit higher, which can be attributed to the more material available and a few other aspects, the glue and things like that. So the 50 kilowatt meter square also gives similar kind of results. As you can see, more higher ignition time, more later picket release time, more flame out, later flame out time, but a higher picket release as well for the form samples. When it comes to the residue, the form samples has a much stable structure compared to the glued ones, as you can see from the figures. Is self-explanatory. Then going into the 300 cross 300 millimeter compartments, we have done a vertical test for this because of the size constraints, and we can see there's similar kind of results. The continuous wall has a later ignition point, higher peak heat release rate time, more flame off time, and a higher peak heat release rate as well. The difference between the two is that the difference from the wall exposed to the fire is around 115 millimeters because of the bigger sample. So it is a bit so that's why the peak heat release rate is a bit lower in these studies. Going into the core structure, as you can see, the sandwich cores and the honeycomb cores both both show that plywood has a higher ignition time, better heat release rate train, lower peak heat release rate, lower smoke production, lower time to total heat release. So basically, the plywood has significant advantages when it comes to different structures, and the formability gives significant differences to the flammability studies. So we can basically combine these results and combine the materials to get a fire retardant plywood structure, which can give even better results. Thank you for hearing me, and this is my email address. If you want to contact me, you can contact me on this. Thank you.